Hello everyone. Today I have the honor to discuss with you about the research results of mobile multimedia communications. The topic I want to share with you today is privacy preserving property prediction for new drugs with MPNN. My name is Jiaye, and I am the first owner of this paper. My contact information has been shown on the screen. If you are interested in my topic, welcome to discuss with me. Next, I will talk about this topic. I will introduce our research results one by one from the following aspects: include introduction, related work, system architecture and basic definition, secure n-party protocols, privacy preserving property prediction for new drugs, theoretical analysis and experiment conclusion. Message Passing Neural Network (MPNN) for learning molecular fingerprints has been considered to be an ideal approach to predict the property of new drugs. Compared with traditional methods, such as density functional theory (DFT), MPNN has better predictive performance and interpretability. Drug Lab can utilize this model to obtain further insights into predicting the properties of new drugs and make more effective improvements. However, the computing power and storage capacity requirements for training such an MPN models are quite staggering. Therefore, instead of building their local server, the drug lab prefer to build the MPN model using cloud computing technology and outsource their new drugs to cloud servers. Besides, the process from drug discovery to market cost on average well over $1 billion and can span 12 years or more. Due to high attrition rates, rarely can one progress to market in less than 10 years. Neither research nor lab wants these new drugs discovery to reveal to some hostile adversary. Therefore, new drug information is a valuable commercial resource for the drug lab. It's necessary to build an efficient, privacy-preserving framework for MPN to predict the properties of new drugs. At present, there are mainly two kinds of encryption technology using in machine learning. One is homomorphic encryption technology, and the other encryption technology based on secret sharing. Although homomorphic encryption technology can perform encryption operations accurately, it's difficult to be applied to machine learning security due to its inefficiency. Encryption technology based on secret sharing has been proposed to be applied on smart IoT devices, mobile sensors, medical image, and so on, because of its lightweight trajectories. But their systems architecture relies on a trusted third party. This is hard to find in practical applications. The traditional machine learning toolkits use PyTorch for training, which has enough efficiency, but there are some limitations in accuracy and data range, which is not conducive to the research of multi-party secure computation. Therefore, in order to solve the above problem, We built an efficient MPNN models and propose a series of secure and high adaptive multi-party protocols. Finally, we make a series of theoretical and experimental analyses on our model. The main idea of secret Xinying is to divide a secret value into the sum of several numbers randomly, and distribute these attendants to each server to ensure that the server doesn't know the original secret value. In this paper, we use the lower corner marks to distinguish the assigned server number, and the upper corner market is the corresponding position of the binary complements of the number. In addition, each server is honest but curious, which means that they will not seek to get confidential value together, but they will not refuse to calculate the date that is benefit to them. This is the assumption that the architecture is secure. From now on, I will introduce secret multi-party protocols one by one, include addition protocol, multi-protocol, and comparison protocol. When executing the addition protocol, each server only needs to calculate the shared value of two attendants owned by itself locally, so that the whole value can be adapted, which is also suitable for subtraction. Next is secure multiplication protocol. Before introduce this protocol, we first introduce how to refresh the secret Xinying without exploding the secret value. The most efficient operation is that each server generates a random value. Send the random value to the designated server, and each server calculates the difference between the random value generated by itself and the received random value. Update the secret Xinying without changing the secret value. This option is not only very efficient, but also can ensure that the server can deduce the secret value according to the historical date and in the subsequent secret Xinying delivery operation, and can limit the date range of secret Xinying. In the implication of secure multiplication protocol, we first refresh the two secret values, and then divide the square attendance equally to each server through the idea of multiplication location law, and limit each server to get as little shared value as possible to ensure that the secret value will not be disclosed. This flowchart will demonstrate how the server can generate a random bit by itself. The main idea is to generate a random number, remove the symbol bit, and change it into a random 1 or -1, and then convert it into 1 or 0 bit. After we get the protocol that can generate random bits, we can use this protocol repeatedly to generate a random number and its complements. With the above protocol, we will subtract a secret value by the generated random number, and convert the calculated result into binary complements. In the complement state, we will convert it into binary complements by binary addition without exploring the secret value. The related calculation process is given in the demonstration. It's worthy note that is in the architecture with a trusted third party. The role of the trusted third party is mainly to generate a random number and the information related to the random number, which will save the operation steps in the previous part. However, as mentioned above, there are some difficulties and security risks in the implementation of trusted third party. In the process of comparison, we only need to transform the two numbers to be compared into complements through the previous protocol. By using the properties of complements and the operation of symbol bits, we can make a secret comparison under secret sharing and ensure that the server doesn't know the result of comparison. After a serious protocol mentioned above, we use the way of fitting to deal with the complex function, transforming the complex function into piecewise polynomial function. Determine the range of fitting function by comparison protocol, and calculate the approximate value of complete function by multiplication protocol and addition protocol. The accuracy of this method is higher than that traditional iterative calculation. This graph intuitively shows how the secret N-party protocol constructs the secure MPNN models. Through three secure protocols, we can build a secure full connection layer, secure element point multiplication, and three secure activation functions, sigmoid, tanh-h, and ReLU. We describe the data flow in MPNN model. In the first part, the message function passing through three layers of fully connective neural network, and the second part represents an update function composed of a Jiaye, and the last part is a readout function composed of multiple fully connected layers and an activation function. We also show the flowchart of the overall encryption of the drug lab in order to more intuitively understand the encryption process of the secure MPNN model. Finally, through experiments and comparison, we discuss our secure MPNN model in terms of correctness, security, and efficiency. The accuracy is 95.36%, and the error mainly comes from the date truncation error and fitting error. We also prove the secret of system model by proving using script. The input and output of the adversary in the distract server are indistinguishable from the real view. Therefore, the MPNN model is secure under the assumption that the servers are honest but curious. In terms of efficiency, our protocol not only improved the efficiency, but also adapt to the system architecture with different number of servers. We also test the performance of the model with different encryption bit lengths and different number of servers, which shows that our model is more practical. Our lightweight model is applied to neural network, which use multi-party secure computing. It supports enough secure bit length and eliminated the third party which is difficult to exist. They are better than previous paper. Finally, our main contribution is to propose a lightweight privacy-preserving drug prediction model, which can adapt to different system architectures and different encryption lengths. At the same time, it has the consideration of accuracy, safety, security, and efficiency. In the future work, we will try our best to solve the inevitable accuracy error and more practical complex protocols to solve more problems. This is the end of my report. For more information, please contact me through this email. Thank you for your listening. Goodbye.